Hello everyone, and welcome back to another GIS lecture video. And in this lecture video, I want to talk about something related to fuzzy membership that we haven't talked about yet. And that's the idea of what do we do once we've converted all of our data layers through these fuzzy membership functions to fuzzy values, right? Or put another way, right? How do we combine our layers to get a final suitability? For the binary suitability, we added them up or multiplied them. For when we had suitability scales, we did that weighted overlay. Well, for fuzzy membership, we actually have a couple of options. And it's important to understand what each option does so you pick the right one based on your data. So for fuzzy membership, combining them, we have what's called fuzzy overlay. Right, so the fuzzy membership function converts raw values to fuzzy values. We then take those fuzzy values and we do some form of fuzzy overlay. And so fuzzy overlay, there are really 5 options. And what I want us to consider is the values for 4 data sets, for 1 pixel from 4 data sets. So fuzzy value, so we have 4 data sets. And these are going to be fuzzy values. We have a value of 0.9, a value of 0.95, a value of 0.5, and a value of 1. Right, so these would be 4 different data sets. These are the fuzzy values that came out. And we're going to talk about the 5 different fuzzy overlay options given these 4 values. Okay. So the first 2 options are what are called logical operators. Logical operators. And these are going to be the logical operator and the logical operator or. Now, when I first learned about these logical operators, I found them a little bit confusing because I immediately think about doing database SQL queries. But if you stick with me for a second, I think we can simplify these to basically mean and means all of the layers matter, right? And so what we're going to say is if all of the layers matter, then we have to take the lowest. So we'll do an or, and. So with or, what happens is we're basically saying we only need one piece of suitable habitat for the whole thing to be suitable. We don't necessarily care which one it is. We just need one suitable category for the entire cell to be suitable. Right? And so in this case, right, what that translates to is take the highest. Right. So if we have these 4 values, 0.9, 0.95, 0.5, and 0.1, and we apply the AND operator, right, we take the lowest. So if we do the AND to all 4 of these, what we get back is 0.1. If we apply the OR operator, where we take the highest because we only need one of them to be suitable for the whole cell to be suitable, we would take the highest, which is 0.95. So that's the two logical options and an OR. Then we have the mathematical options, the math operators. And for the math operators, we have product, sum, and gamma. Now, for product, right, that's pretty simple. It's the multiply them together, right? And so if we were to actually execute that, right, 0.9 times 0.95 times 0.5 times 0.1, right, 0.9 times 0.95 times 0.5 times 0.1, what we end up getting is 0.0 0.04275. So product So here's the problem with product, and the reason why we don't use it very often, is that what happens is product strongly weights layers with low fuzzy values. Right? Because just think about, even if we just had two, let's digress for a second. Right? If we had one that was 0.9 and one that was 0.1, so we had a high suitability layer and a low suitability layer, right? And we multiply those together, we get 0.09, right? Which is even lower than the lowest suitability, right? So when you use product, you heavily weight low suitability layers, and you also heavily weight the number of suitability layers, right? If you have a lot of variables and you do product, your end result is always going to end up lower just by having more suitability layers, which may not necessarily be what you want, right? Because unless they're all one, every time you add a suitability layer, you're multiplying by a fraction, which always ends up with a smaller number. So product tends to have low values in general because lower suitabilities are highly weighted, and also the more layers you have, the lower your final suitability is going to be. Right. Next we have sum. So sum does not mean add them together. Sum actually means, right, 1 minus the fuzzy value times 1 minus the fuzzy value times 1 minus the fuzzy value for as many layers as you have. Okay? And so this can be a little bit confusing. Let's go ahead and look through an example of what this looks like using our data sets, right? So we have 0.9, we have 0.95, we have 0.5, and we have 0.1. So it's 1 minus, 1 minus, 1 minus, 1 minus. So this is 0.1, 0.05, 5.9. Then we're going to multiply them together. And we get a value of 0.00225, and then it's 1 minus that. And we end up with a final suitability of 0.998. Right, so you can see that you end up emphasizing, sum emphasizes high suitability. Right, so sum, we get a value of 0.998. Right, so sum and or tend to give you higher suitability. Right, you tend to weigh more heavily on the few layers that are suitable. And product tend to give you lower suitability, as you tend to weigh the layers with low fuzzy values. The fifth operator, so let's quickly outline, right? We have and, or, product, sum, and gamma. Gamma is a combination of product and sum. And what gamma is, the equation for gamma is the sum calculated using the sum equation to some power we'll call g for gamma times the product to 1 minus whatever that gamma you picked was. Now, why would you choose gamma? Because what gamma is going to do is it's going to give you fine scale control, finer control over the end result that you get by balancing out this idea of weighing low values and weighing high layers, right? Because again, product, you tend to highly weight low fuzzy values. With sum, you tend to highly weight high fuzzy values. With gamma, by choosing a gamma parameter and tweaking that gamma parameter, you end up balancing out those two to give you a lot of fine scale control. So let's go ahead and look at what this would look like for our equation here. Let's set a gamma equal to 0.6. Right. So what we would do is we would have gamma equal to 0.6. That's going to be sum, which we said was 0.988, raised to the 0.6, times our product, which we said was 0.04275, raised to the point, raised to the point 0.4, right? Because 0.6, 1 minus 0.6 is 0.4. Right, and so if we do that, 0.988 raised to the 0.6 times 0.04275 raised to the 0.4 what we end up getting for gamma, right, is 0.2813. And so you see with the gamma, right, we're not nearly as high as the sum, but we're higher than the product. And if we change the gamma, right, if we change the gamma closer to 1, we're going to weight our values, we're going to weight this part higher. So we're going to end up having a higher overall suitability. If we set our gamma lower, we weight the product more heavily, which means we're going to weight the lower suitability values more heavily, which means we would end up with a lower overall suitability. So hopefully this makes sense, the way that we can combine our individual layers using fuzzy overlay, one of the overlay options, to end up with different final suitability values. And just to wrap everything up again, circling all the way back to the beginning of how do we actually interpret these, right? A value close to 1 means high suitability. A value close to 0 means low suitability. So our end result, regardless of which fuzzy overlay method you use, is going to be interpreted the same way. So hopefully that makes sense. And as always, if you have any questions, please reach out. Thank you.